Okay. So let's start with the true-false questions. Start with number 1. Increased grain size tends to make a ductile metal stronger. This is false. It makes a ductile metal weaker, or you can say decreased grain size tends to make a ductile metal stronger in this case. Second question. Creep is a failure mechanism that results from cyclic stress at elevated temperatures for prolonged periods of time. This is not correct. It's fatigue, which is a failure mechanism that results from cyclic stress at elevated temperatures. I'm sorry, not fatigue. Creep is a failure mechanism that results from constant stress at elevated temperatures. Okay, for prolonged periods of time. If you say like fatigue is a failure mechanism that results from cyclic stress, but not necessarily elevated temperatures. It may happen at room temperature as well, fatigue. So this is a false statement. Third question, in general, the stress at the failure point on an engineering tensile stress strain curve is typically higher than on a true tensile stress strain curve. This is false because it's typically lower than on a true tensile stress strain curve. And this is because the engineering tensile stress strain curve takes into consideration the starting cross-section area, right? So during the tension test, you increase the load, right? There's a stress and strain, but when you calculate stress and strain, for stress, you take into account that initial cross-section area. What was stress? Stress is equal to force divided by cross-section area, right? F over A. So that A is actually A0 in engineering tensile stress strain curve, which is a constant, which is the starting cross-section area. But on a true tensile stress strain curve, that cross-section changes throughout the test. So you are loading the sample while the sample is plastically deforming. In the plastic deformation area, there is a change in the cross-sectional area, right? There is necking, and the cross-section area decreases. So that true tensile stress strain curve takes into account that instantaneous cross-section area. So because of that, force remains constant, but true tensile stress strain curve takes into consideration that instantaneous cross-section, whereas engineering takes into account the starting cross-section area. So in true tensile stress strain curve, since we are looking at a smaller cross-section area, right, the stresses are supposed to be higher than the engineering tensile stress strain curve in the plastic deformation region. Fourth question, resilience is a measure of the total capacity of the material to absorb energy up to the failure point. This is false. It is toughness, which is a measure of the total capacity of the material. Cold rolling a metal, that is by deforming, by compressing and squeezing between two rollers, decreases its dislocation density. This is false. It increases the dislocation density, right? Critical resolve shear stress represents the minimum shear stress required to initiate slip. This is correct, and it's a function of loading direction relative to the slip direction, and this part is false because it's independent of the loading direction. It's a material property. So overall, this is a false statement. Number 7. Recrystallization is the formation of a new set of strain-free and equiax grains that have low dislocation densities. This is true. SN curves illustrate the evolution of creep strain in metals as a function of time. This is false. SN curves illustrate the evolution of, not evolution of, like they illustrate the fatigue life as a function of alternating stress. As the percentage of cold work of a material increases, the yield and tensile strengths increase. This part is correct. While ductility and elastic modulus decrease, this part is false. because ductility decreases, but elastic modulus does not change, right? So with any percentage of cold work, elastic modulus remains constant. Interstitial diffusion involves the interchange of an atom from normal lattice position to adjacent vacant lattice site or vacancy. This is false because it's not interstitial diffusion, it's substitutional diffusion. Like diffusion of substitutional atoms, not interstitial atoms. This is a false statement. All right, that's it for part A. Any questions? You can type in the chat or unmute yourself and ask. Let's continue then. Part B is multiple choice questions. A single crystal initially has the atomic arrangement shown to the right. A small load is applied in tension, and the sample elongates in the vertical direction. After removing the load, the crystal remains elongated. So this statement is important. After removing the load, the crystal remains elongated. That means there is plastic deformation, right? The material is plastically deformed, irreversibly deformed. Which of the following best represents the crystal structure in the material after deformation? So we need to find the structure which shows a sign of plastic deformation, right? So looking at A, we don't see any plastic deformation. If there were any plastic deformation, we would see like shifting of these atoms. We need to see a sign of slip, basically, the slip mechanism. This part A, the choice A, is only elastic deformation, right? You see a stretch of these bonds here. This is elastic deformation, a sign of elastic deformation. So when you unload this material, it's going to go back to its original unloaded state. Let's look at C. C is the same as the starting point. There is no load, nothing, there is no change between these two structures. B and D, let's look at B and D. In B, this red line indicates the slip direction. Looking at the microstructure, there is slip. You see there is slip here. This portion of the lattice is slipped upwards, okay? So this is fine. It's a sign of plastic deformation, but this is not possible. I mean, this slip direction cannot be along this line. And that's because of the Schmidt factor. Okay, if this is the slip direction, then the slip plane should be on this line, right? Think of it like it's perpendicular to the screen, and this will be the normal direction of the slip plane. And this is our load, right? Loading direction. And if you remember from the Schmidt's factor, you look at these cosines of two angles. One of that angle is the angle between the load and the slip direction. And the other angle is the angle between the load and the normal to the slip plane. So if any of these angles is equal to 90 degrees, then the Schmidt factor will be 0, right? Sm is the cosine of those two angles, right? If any of those two angles is 90, then because cosine 90 is 0, then Schmidt factor will be 0. If Schmidt factor is 0, there won't be any result shear stress on that particular slip system, and there won't be slip. So this is not possible. So we eliminate B, and the answer is D. Okay? So for slip to occur, the angles, like the two angles we just talked about, should be between 0 and 90 degrees. All right, let's clear this. Let's go down. Which set of planes and directions represent the slip system in FCC materials. FCC materials, the closed back plane is 111 plane, right? Family of planes, and the closed back direction is 110. The correct answer is A. Which one of the following represents the Burgers vector for unit dislocation in BCC materials? Burgers vector will be along the closed back direction, right, in BCC, and the closed back direction in BCC was 111 direction. And the correct answer is C. The concentration of defects and imperfections in a crystal lattice depends on the temperature and deformation history of the sample. Correct answer is D. Decreasing the average grain size of a ductile alloy tends to increase the strength and hardness of an alloy, make the alloy less ductile, and not affect the elastic modulus of the alloy. So this last part is critical. Okay, so changing the average grain size or changing the cold work, as we mentioned before, does not affect the elastic modulus. Any questions from part A and part B? All right. I mean, if you have any questions, just type in the chat. Okay, part C, short answer questions. Of those metals listed in the below table, which will experience the greatest percentage reduction in area and why? So assuming constancy of the volume of material during plastic deformation, the material with the highest strain at fracture or ductility will experience the greatest percentage reduction in area. That makes sense, right? If a material elongates more than the others, then it's going to have the larger percentage reduction in area. So which material is the answer? I did not write the answer here. We are looking at strain at fracture. So this material B, which has 0.4 strain at fracture, which means 40% strain at fracture, will experience the greatest percentage reduction in area. Which is the strongest and why? Material B is the strongest with the highest tensile strength. Like to decide on which material is the strongest, you look at the tensile strength. So it's material D. Which is the stiffest? To measure the stiffness, you look at elastic modulus, right? Elastic modulus of a material, the slope of the initial region, the linear region, which is the elastic modulus, tells you about the stiffness of the material. The larger the elastic modulus, the more stiff the material is. So we look at the last column on the right, and we see that material E is the stiffest because it has the largest elastic modulus. What was the answer to 1A? 1A. The answer to 1A is material B. Can I write here? Yes. Okay. A single crystal of metal is oriented for a tensile test such that its slip plane normal makes an angle 63.6 with the tensile axis. Three possible slip directions make angles of 30, 48, and 78 degrees with the same tensile axis. Which of these three slip directions is most favored? I mean, this is a very straightforward question. You just need to find the Schmidt factor for each of these slip systems. The angle between the loading axis and the slip plane normal stays the same for the three slip systems, which is 63.6. The only change is the angle of the slip directions between the loading axis. And if you look at the Schmidt factor formula, so we find the Schmidt factor for each of these three slip systems. And you see the slip system which has the highest Schmidt factor, in this case, the lower angle. So the lower the cosine, the angle, the higher the cosine will be, right? So the 30-degree Schmidt factor, the slip system will have the highest Schmidt factor, right? 0.385. So slip will take place along the direction of 30 degrees. So slip will take place on the slip system. 63.6 with the tensile axis and 30 degrees with the slip direction. Okay. Label fatigue limit on the SN curve below. Also explain which region is safe and which region is not. So the stress amplitude at which the SN curve makes a plateau, this straight portion, is the fatigue limit of this material. Okay. So fatigue limit, by fatigue limit we mean below the stress level, which is somewhere here, right? Let's call this S3. This is the stress amplitude. If you load this material to a cyclic stress, which is a stress amplitude lower than S3, then this means basically you can have infinite fatigue life. You can cycle this part material with that alternating S3 stress, and it's gonna last forever. That's the meaning of fatigue limit. So some materials have this fatigue limit, meaning that you see this plateau, this flat region. This is the case for steels, for instance. But some non-ferrous alloys, like copper, aluminum, they don't show this plateau. Instead, they exhibit this kind of behavior. Okay. The stress amplitude will keep decreasing with increasing cycles to failure. So there won't be any flat region, and there won't be a fatigue limit for some of these non-ferrous alloys. Also explain which region is safe and which region is not. The region above the fatigue curve, SN curve, is unsafe. And below, underneath this curve, is the safe region. So what does this mean? If you take any point below this SN curve, let's say I choose this point, okay? And I look at the corresponding alternating stress value, which is, let's say, S3. At this stress amplitude, I can basically have infinite cycles to failure. Let's give another example. Let's look at this point, for instance. Let me clear it. Let's look at this point here. Okay. So if I draw this vertical line, dashed line, and this horizontal line, this point corresponds to a stress amplitude, let's say S3, which is larger than S2, right? And at this amplitude, stress amplitude, I can have 10 to the power of 4, which will be okay. I can get 10 to the power of 4 cycles before failure. I can even get more than that, right? At S3, stress amplitude. So what is the maximum of number of cycles before failure? I extend this horizontal line, and wherever I intersect this SN curve, I draw this vertical line, and this is the cycles, number of cycles I can get before failure. So it's slightly larger than 10 to the 5, okay? And if I want more cycles, like 10 to the 7 cycles, I cannot use this S3, right? This is too large. I mean, this is too large of a stress to be able to get 10 to the power of 7 cycles to failure, because this time it's going to be in this region, which is unsafe. So if I want 10 to the 7 cycles, I need to decrease the stress amplitude. So I need to go down here at least, which is smaller than S2. Okay. All right. Any other question here? Okay. Which region is safe, which region is not? We explained all this. You can read these extra notes on your own. I'm gonna upload this after the session to Canvas. Fourth question, if a crystalline material has only one slip plane and it's loaded in the direction normal to that slip plane, will this material yield? Why or why not? This question is very similar to what we have seen in the first part, first question of part B, right? This question. So again, we look at the Schmidt factor. We try to find the Schmidt factor. This is the loading axis, right? This stress is, this material is loaded in this direction. And this is the slip plane. This dashed green line is the slip plane. And this is the slip direction. The arrows show the slip direction. But normal to the slip plane is this, right? So the direction which makes 90 degrees with the slip plane. This is my normal to the slip plane. So note that the angle between the loading axis and normal to the slip plane is 90 degrees. So from the Schmidt factor, cosine 90 is equal to 0. So there won't be any shear stress. We can conclude that there won't be any shear stress on this particular slip system. Remember the formula for the resolved shear stress, right? Sigma times cosine of lambda and cosine of, I don't know, mu. So these are two angles, the angle between the loading axis and the slip direction, and the angle between the loading axis and the normal to the slip plane. If either of these angles is 90, then the cosine becomes 0, and this resolved shear stress becomes 0. There won't be any resolved shear stress on that particular slip system, and there won't be any plastic deformation. Okay, let's continue. Write 3 strategies for strengthening pure copper. Briefly explain how each strategy works. 3 strategies are common strategies: grain refinement, solid solution strengthening, and work hardening for pure copper. You can read this information on your own later. In the creep strain versus time curve shown below, list the temperatures from highest to lowest. This plot shows creep strain on the y-axis and time on the x-axis. If you remember, we have 3 different regions in the strain versus time plot, right? We have the primary creep, secondary creep, and tertiary creep. So looking at this green plot, this region is the primary region, and this region is the secondary region, and this is the tertiary creep region. So we know that with increasing temperature and increasing stress, remember that creep strain takes place at elevated temperatures, more than 0.4%, and not more than 0.4 times the melting point of a metal, right? If we are talking about creep in a metal. And at constant stress levels. And with increasing stress or increasing temperature, the time to rupture, which is shown with this X, will decrease, right? Because the material will creep faster and it's gonna fail earlier. So if you pay attention, you will see that with increasing temperature or stress, the region which is most affected by this increase in temperature or sigma, which is the stress, is the secondary region, right? Steady state creep or secondary creep. So this portion will decrease. The time for the secondary state, secondary creep or steady state creep will decrease the most among these three regions. This is not asking the question, but it's just an extra information. So the question asks us to list the temperatures from highest to lowest. And we know that T3 will be larger than T2, which will be larger than T1. You can say the same for stress. Stress will be, if we keep the same temperature, stress 3 will be larger than stress 2, which will be larger than stress 1. Okay. You are developing a new alloy for a car bumper. You have developed three different materials, A, B, and C. Which one would you use for a car bumper and why? So the answer is you would ideally want the bumper to have a combination of good strength and ductility, leading to the highest toughness value. Remember, toughness was the area underneath the stress strain curve, right? So the higher the toughness value, the higher the energy absorption, which is the desired property for a car bumper. So therefore, the best choice would be material B, right? For material B, you can see that this area is the largest, this shaded area. The area underneath the stress strain curve for B is larger than A or C. So C is the typical response for a polymer. Okay, low strength and high strain. Polymers are very ductile materials with low stress, low strength values. And A is probably a ceramic, right? Because you only see this elastic region. There is no sign of plasticity like B. And it fails at a high stress value. Ceramics are strong, but they don't show ductility. They are brittle materials. And obviously, you don't want a ceramic material as a car bumper. Okay, let's continue with problems, part D. Figure below shows the deformation of a single crystal for the given loading and slip conditions, and critical resolved shear stress is given as 8.9 MPa, which is a material property. We are asked if the single crystal will yield under this application of a load, and what is the yield stress. So we are given the slip system, right? We are given the two angles, lambda and phi. So phi is the angle between the loading axis and normal to the slip plane, and lambda is the angle between the loading axis and the slip direction. We just need to put these values into the resolved shear stress formula. So we apply an external stress and we want to find the resolved shear stress on this slip system. Okay, so we use the formula tau r is equal to sigma times the Schmidt factor. Sigma is given 44.8, and we know the angles. So the resolved shear stress is 18.3 MPa. So since this resolved shear stress 18.8 and 18.3 is larger than 8.9, we can say the single crystal will yield. Okay, so since it's larger than the critical resolved shear stress, the material is going to yield. And how do you find the yield stress? So for yield stress, again, we use a different version of this formula, resolved shear stress formula. In that formula, we just need to plug in the critical resolved shear stress in the place of tau r, and sigma will be the yield strength. Okay, once you work that equation, you will find sigma y, the yield strength of this material, as 21.7 MPa. So that's the yield strength for this single crystal. I mean, right now we are applying 44.8, but if you apply it even 22 MPa, this single crystal would yield. Okay, a question on stress strain curve. Figure below shows the tensile stress strain curve of a cylindrical rod made from an unknown alloy. The rod has a cross-section area of 0.5 times 10 to the minus 3 meters square. So we are asked 6 questions. First question, what is the maximum load that this rod can support, yet still recover its initial shape when the load is removed? So read the question carefully because we are asked the maximum load, okay? This part is important. Let's see the answer. What is the maximum load that this rod can support, yet still recover its initial shape? So what does this mean? We need to stay in the elastic region, the elastic deformation area. So the material should not be loaded in the plastic region. So basically, we need to stay in this linear range, okay? So what I need to do is I need to find that load value corresponding to this maximum stress value in the elastic region. Since we want the rod to recover its initial shape when the load is removed, stresses should be in the elastic range. Looking at the inset, the elastic limit is around 320 MPa. Okay. To convert the stress to load, you see 320 MPa is this point here. And I need to convert the stress level to the load, right? And remember the definition of stress. Stress is force divided by area. And I can calculate the force as stress times the cross-section area, right? Remember the question asks us about the maximum load, not the stress. If the question asks us the stress, maximum stress, then the answer would be 320. So doing this calculation, force is found as under 60 kilonewtons. So for this kind of questions, I mean, this, you can definitely see this is the elastic region, the linear region, right? But I will also accept the load, any load below the yield stress. So how do you find yield stress? Let's see if that's asked in the questions. I'll come back to this question later, okay? I'll come back to this A part later. So what is the value of modulus of elasticity? Remember, the modulus of elasticity can be found as the slope of this region, okay? The slope of this region. If this is alpha, we want to find tangent alpha, right? Which will give us the slope of this region. One easy way to find the slope is you need to pick 2 points, right? I suggest you pick this as the first point to make the calculations easier. 0, 0 should be your first point. And pick any 1 point on this linear region. Take, for instance, this point corresponding to 200 MPa. And this will be approximately 0.001, right? 001. And the elastic modulus is 200 divided by 001. Pay attention to the units. It's going to be 200 MPa divided by 0.001. And it's going to be about 200 gigapascals. Let's see if it's correct. I picked a different point. See, I picked this 320 MPa and found the x-intercept as 0.0015, which gave me 213 gigapascals. It really doesn't matter. I mean, even if you got 200 gigapascals in the exam, it would still count as correct. There will be a set tolerance for these kinds of questions, where like taking the values from the x and y axis will be very much dependent on the person who is taking that value. Okay, so the third question is, the rod has an initial length of 0.5 meters. What is the new length of the rod once it's placed under static tensile stress of 350 MPa? So this is the important part of this question is under a static tensile stress of 350 MPa. So the rod is loaded, but it's not unloaded, okay? We just keep it under load. And we need to find this 350 MPa. So it will be somewhere here, right? 350 MPa. And corresponding to that 350 MPa, the strain will be 0.002. So this is the strain 0.002, which is 0.2%. So the new length of the rod, I'm just gonna use the definition of strain, right? I know the original length of the material. The strain will be 0.002. From the definition of strain is equal to delta L divided by the original length, and the elongation is found as the original length, which is 0.5 meters, times the strain, which will give me 0.001 meters. So the new length is, final length is the original length plus the elongation due to that 350 MPa, and it's going to be equal to 0.501 meters. So what is the value of tensile strength? Remember, the tensile strength is the highest point on the stress strain curve. So you can see here, the tensile strength is about 500 MPa, right? That's the highest point on the stress strain curve. So what is the value of toughness in joule per cubic meter? A rough estimate is acceptable as long as you show your calculation. So to find this, you need to find the area underneath this entire curve, right? So one easy method to do this is you separate this region into rectangles or triangles. I mean, you can give a very approximate value here. So for instance, I approximated basically, actually it is, let me see, what is my approximation? My approximation is, I picked this point, 450 MPa. I picked this rectangle, okay? I calculated the area of this rectangle from this length is 0.18. And this height of the rectangle is 450, okay? So I multiply these two values, 0.18 times 450, and this will give me the area of this rectangle, right? I'm gonna approximate it approximate it to the area of the stress strain curve, area underneath the stress strain curve. So what is my result? You can do a similar approximation. You can take different rectangles. So based on my approximation, the area of the rectangle is 450 times 10 to the 6 Newton per meter square, which is pascals, times 0.18 meter per meter. Pay attention to the units here. I guess the question asks us joules per meter cube, so you have to convert the stress to pascals and strain to meter per meter, which is going to be the same anyway. So this multiplication will give me the toughness value, the area of the rectangle, as 81 joules per meter cube. Okay. So can you estimate the type of this alloy? I mean, I cannot ask this question in the exam unless I give you a table showing the elastic modulus of different alloys. you can actually estimate the type of this alloy as long as you know the elastic modulus. Okay, so in the first part, part B, we calculate the modulus of elasticity, right? Which was about 200 gigapascals. And if I gave you a table of different metals with different elastic modulus, you could tell me the type of this material. For instance, steel has an elastic modulus of 210 gigapascals. Okay, so since we found out the elastic modulus about 200 gigapascals, 213 gigapascals, we can say this material is a steel without knowing it's a steel by looking at the stress strain curve and calculating the elastic modulus. You can tell me the type of the material. Of course, as long as you have access to that table or you somehow know the elastic modulus of different materials, if that information is in your head. Okay, last two questions, or yeah, this will be our last question. This one is on simple fracture. A specimen of 4340 steel alloy having a plane strain fracture toughness of 45 is exposed to a stress of 1000 MPa. Will this specimen experience fracture? If it's known that the largest surface crack is 0.75 millimeters long, why or why not? Assume that the parameter y has a value of 1. So the most important part in this question is the type of this crack, surface crack, okay? If you remember from the slides, we have this part, right? If it's pulled in tension with a force F, let's say, remember the slides, and if there is a crack like this in the material, this is an internal crack, right? And the size of this crack is given by this value, which is 2A. So for internal cracks, the size of the crack is always given as 2A. Whereas for a surface crack, if I have a crack on the surface, the size of this crack is given as A. Okay, this length is A. So why is this important? Look at this formula here, the fracture toughness formula. The critical stress is equal to the fracture toughness K1C divided by Y, the material parameter, and the square root of pi times A. So this A is the dimension of the crack, right? In this equation, it's A. So let's look at the question. The question says it's a surface crack, right? Surface crack is 0.75 millimeters long. And the surface crack, the length of a surface crack is given by A. So we know is A is equal to 0.75 in this question. Okay. So the tricky part is if I ask you in the question, not surface crack, but an internal crack. Internal crack is 0.75 millimeters long, then that internal crack will be defined by 2A, and A would be, in that case, 0.75 divided by 2, right? So depending on the type of the crack, whether it's a surface crack or an internal crack, the value you are going to put here will change. So for this question, we are given a surface crack. Let's see if the specimen will experience fracture. We just plug in the values. We are given the K1C value, 45. Y is given 1. We write pi, and the surface crack is given. If we do this calculation, we find the critical stress as 927 MPa. So that's the critical stress. if you load the material larger with a stress larger than this value, the material is going to crack. The crack will propagate, the existing crack. Okay, so the answer is fracture will most likely occur, not most likely, will occur, because this specimen will tolerate a stress of 927 MPa before fracture, which is less than the applied stress of 1000 MPa. Okay. What if this was an internal crack? Let me ask you this question. Instead of a surface crack, let's say it's an internal crack. So I use this value of A this time, 0.37. If I plug in 0.375 here, which is half, right? Since the denominator will be smaller, I'm gonna get a critical stress value larger than 927, right? So make that calculation. I haven't done it. If it's larger, if sigma critical is larger than 1000 MPa, then this means fracture will not occur for this kind of crack because it's going to be larger than 1000 MPa, right? No, wait. Stress is 1000 MPa. I'm sorry. Okay. No, that's okay. Yeah. For that internal crack, if this, let's say, I did not make the calculation, but let's assume I found this as 1200 MPa. Okay. What does this mean? That's the tolerance of this material to an internal crack. Since the applied stress is 1000 MPa, in this case, fracture will not occur because it's smaller than 1200 MPa. Is this clear? This is a bit tricky. The type of the crack will determine the tolerance of the material to crack propagation. So pay attention to the type of crack if I ask you a similar question in the exam. Okay. Let's continue. A specimen of S590 alloy. The length of this alloy is given, 750 millimeters, is exposed to a tensile stress of 80 MPa at 815 degrees Celsius. Determine its elongation after 5000 hours. Assume that the total of both instantaneous and primary creep elongation is 1.5. So note that the material is exposed to a constant tensile stress of 80 MPa at a very elevated temperature. So this will be a creep problem, right? And the question also mentions about creep, so it's easy to understand it's a creep problem. So remember we had this creep strain versus time relation, right? This is strain, creep, and this is time. Remember we had these three regions. First region, actually not, let me draw it again. Let's draw it again. Okay. So we have these three regions. This is time, and this is creep strain. First region, second region, third region. Well, actually, before starting this first region, we load the material, right? You apply a load to the material before holding the load at a constant value for prolonged time. So as soon as we apply this 80 MPa stress, there will be an instantaneous deformation, right? So that deformation is this pink deformation, which happens at t equal to 0, because that's instantaneous. You immediately load the material, right? You suspend the load, then that's the instantaneous strain. And we keep this load and we wait for the time to pass. And these three regions, the primary region, secondary region, and tertiary region. This is the primary region, right? We will have primary creep here with a decreasing strain rate. As you can see, it's a parabolic relation. The creep rate, the tangent to the curve at each time is decreasing, right? That means decreasing creep rate. So the creep rate decreases in the first region, primary region, and this is a linear region, which means the creep rate is constant, the slope is the same. And in the third region, where we have sudden fracture, rupture, in the tertiary region, we have increasing creep rate, because at each time, the tangent, the slope of this line, at each point increases, right? That's an increasing creep rate. So the question gives us the total of both instantaneous and primary creep elongation is 1.5. So basically, I know the strain. This one is given. And I also know this primary region, the strain coming from this primary region. What I want to find out is the creep strain resulting from this green. I need to find this strain shown by this green arrow, which is the strain coming from this steady state region, secondary creep region. So these two are given. This is given, this is given. I need to find out this steady state creep. So let's look at the data. Tensile stress of 80 MPa is, I'm going to use this plot because you see this is steady state creep rate. So this x-axis gives me the creep rate in region number 2. So stress is given, 80 MPa, and temperature is given. This temperature, 815 degrees Celsius, I'm going to look at this red curve. And if I draw this horizontal line, I find this intersect. And let me draw this vertical line. And this x-intercept will give me the steady state creep rate. What is that creep rate? That creep rate is found from the x-intercept approximately as 5.5 times 10 to the minus 6 times hour to the power of minus 1. So that's the creep rate. How do you find the creep? I mean, you have the rate of the creep, you need to multiply by time, right? Elapsed time. So the question gives us the time. We are asked to find the elongation after 5,000 hours. All I need to do is multiply the creep rate, which is given with this unit, hour to the power of minus 1. If I multiply this by 5,000 hours, I'm going to find the creep, steady state creep, after 5,000 hours, right? Because I know the steady state creep rate. So my answer is, for the second region, the strain rate, not the strain rate, the strain is 0.0275. And I found this value by looking at this plot, by finding the intercept from the red curve and 80 MPa stress value. So that's the strain, sorry. And we need to find the elongation, right? We know the strain due to steady state creep. And remember the definition of strain. Strain is elongation divided by the original length. If I rewrite that equation, the elongation is the original length times the strain we know the original length, which is 750 millimeters. And this is the creep strain. And this will be the elongation. It's a huge elongation, right? It's 20.6. So the starting material is 750 millimeters. If I suspend the weight, which is going to cause 80 MPa stress in this material, and if I suspend that weight for 5,000 hours, this material is going to elongate by 20.6 millimeters due to creep. Okay, but this is not the answer. What is the answer? Let's read the question again. Determine the elongation after 5,000 hours. So we need to find the total elongation, not only the elongation due to steady state creep. We found the creep due to steady state. We found the strain due to steady state creep. We need to add to that value the elongation from instantaneous and primary creep, which is given as 1.5, right? So the total elongation is therefore 20.6 plus 1.5, which is 22.1 millimeters. So that's the total elongation, including the instantaneous deformation, primary creep, and secondary steady state creep. Okay, that's it. That's it for this session. Do you have any questions? I'm gonna stop recording right now.